In this video, we're going to take a look at some sample test questions related to solving absolute value equations and solving absolute value inequalities. The first example we have here is the absolute value of x equals 25. So we have a nice simple expression in absolute value, and then on the other side we have a positive number. In that situation, we can just drop the absolute value sign, and one of our solutions is going to be x equals 25, and we'll get another solution at x equals negative 25. So we can write these answers using set notation, using a brace, curly brace, to start a list of numbers. We can write the list 25, negative 25 as the solution set. In this second example, things are a little more complicated. We have an absolute value expression, the absolute value of x plus 3, but then also minus 4 on the same side of the equal sign. And we want to determine when that equals 10. So the very first thing we have to do is add 4 to both sides before we deal with the absolute value sign. Now we have the absolute value of x plus 3 equals 14. So similar to the first example, we now have an absolute value expression, a pretty simple linear absolute value expression set equal to a positive number. Since the number is positive, we can drop the absolute value signs and write this as x plus 3 equals 14 and x plus 3 equals negative 14. So solving these two equations, we simply subtract 3 from both sides of each equation, and we end up with solutions x equals 11 and x equals negative 17. So to describe our final answer in a similar way, we can use set notation. 11 and negative 17 are the two solutions. To double check our work, we could take those values and plug them back into the original expression and see that they make the original expression true. There are several approaches we can take to solve absolute value inequalities. The method I'd like to describe in this video starts by solving the related equation. So we can solve the absolute value of 2x plus 3 equals 1, and then use that to describe solutions to the problem that we have. The absolute value of 2x plus 3 is greater than or equal to 1. So notice that we have a nice linear expression, a simple linear expression 2x plus 3, and that's set equal to a positive number. And so as we did in the previous examples, I can drop the absolute value, and I get the equation 2x plus 3 equals 1 and 2x plus 3 equals negative 1. Solving each of those, I first subtract 3 from both sides of each equation to get 2x equals negative 2 and 2x equals negative 4. And then we can divide both equations by 2, divide both sides of both equations by 2, to get x equals negative 1 and x equals negative 2. So my next step, I want to plot these points on a number line. So I'll just sketch a number line. Negative 2 is the smaller point, so I'll put that to the left of negative 1. Now notice that these two values, they split the number line into 3 intervals, and the solution is going to be some combination of those intervals. If we look back at the original inequality, since this was a greater than or equal to inequality, since the absolute value has to be greater than a positive number, we can determine that the solution is going to be a disjunction, which in the case of absolute value means that the solutions are either going to be to the extreme right end of the number line or to the extreme left end of the number line, because we need the absolute value to be big, and so that's going to happen far to the right or far to the left. So looking at our graph, I know that the solution is going to be everything above -1 and everything below -2. Since equality is allowed, I'm going to put solid dots at those boundary values. Using interval notation to describe the solution, we get -infinity to -2 with a bracket, and then union -1 to infinity. The next example is going to work in very much a similar way, but this time we have a less than symbol. So let me identify at the start that our solution is going to be a conjunction, and for an absolute value, a conjunction is going to be values that are between two boundary points. Solving the related equation allows us to find those boundary points. So I'm going to solve the equation, the absolute value of 2x minus 1 equals 5. So I'm going to point out one more time that I have a linear equation here that's equal to a positive number. So I can split that into two simpler equations. 2x minus 1 equals positive 5, and 2x minus 1 equals -5. For each of those equations, I can add 1 to both sides. That gives us 2x equals 6, and 2x equals -4. And then we can divide both sides of each equation by 2 to get x equals 3 and x equals -2. So to figure out the solution, I want to plot those points on a number line graph. I get -2 to the left of +3. And since the original inequality required the absolute value to be less than a certain number, the solutions are going to be between those two boundary points. Again, equality is allowed, so I'm going to put solid dots at each of the boundary points to show that they're included. And using interval notation to describe our solution, we get -2, 3 with brackets on both sides. And here's another example. I want to first solve the related equation. The absolute value of -4x minus 2 is equal to 6. Because we have a positive number on one side and simply an absolute value of a linear expression on the other, I can write this as -4x minus 2 equals 6, and -4x minus 2 equals -6. I can add 2 to both sides of each equation. Get -4x equals 8, and -4x equals -4. Dividing by -4 gives us x equals -2 and x equals +1. And let me point out one of the reasons why I like changing to the related equation is now we divide it by a negative. If we had kept it as an inequality, we'd have to worry about how the inequality changes direction. But when we think of these as just boundary points, we don't need to worry about that. It kind of happens automatically. +1 is going to end up to the right of -2 when I plot those 2 points. And then looking at the original inequality, we see that it is a less than symbol. So we can think about, does that mean that we'll have the extremes or the in-between points? Since it's a less than symbol, we're going to have the in-between points. because less than corresponds to the idea of a conjunction. In this case, equality is not allowed, so I'm going to put open dots at the boundary points. And our solution in interval notation is -2, 1, with parentheses on either side. If you're concerned that you didn't choose the interval correctly, we could always use test points to check our work. 0 is a value in between -2 and +1, so when x equals 0, it should satisfy the equation. So I get the absolute value of -4 times 0 minus 2. If we evaluate that, we get the absolute value of -2, which equals +2, and that's in fact less than 6. So it's a true statement for 0, which means that it's going to be a true statement for every value that is in the same interval as 0. So for any value between -2 and 1. Now, in our next example, we need to think carefully. In our preceding examples, we had the absolute value compared to a positive number. In this example, we have an absolute value of x minus 3 compared to a negative number. And so right away, there should be alarm bells that go off, because this is negative. Absolute value signs are always non-negative. So it doesn't make a lot of sense to think about the related equation, the absolute value of x minus 3 equals -2, because this equation is going to have no solutions, because an absolute value expression can never be negative. So the answer comes down to the direction of the inequality. In this case, we have a greater than symbol. Absolute values can never be negative, which means they're always positive, or maybe sometimes they're equal to 0. In either case, it's always going to be greater than -2. So this expression is always greater than -2. And so the solution is going to always be true. We have this nice linear expression inside the absolute value. What comes out of that absolute value is always going to be positive, or possibly equal to 0, but never negative. So every real number is going to be a solution to the inequality, and we can describe this in interval notation as -∞ to infinity. Of course, we put parentheses on both sides because we never get to infinity.